if this works, this is a work in progress. But if the ideas that we have work, this will offer a new paradigm in structural and material design.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Podker. Materials science and engineering explores the basic structure, properties, and behavior of materials to create goods that benefit society. Within that field are a special class of engineered materials that exhibit properties not generally found in nature, called metamaterials. We're joined by Glaucio Paulino, the Margarita Engman Augustine Professor of Engineering at Princeton University, whose group develops emergent materials and structural systems, including one that can change its structure to move, expand, and deform using a magnetic field. Professor Paulino, thank you so much for joining me today.
You are very welcome. I'm glad to be here.
I'm glad to be talking to you about your work today. I want to start with kind of a broad definition. What is a metamaterial robot?
All right, it's a robot made with a metamaterial. And what is a metamaterial? It's a special material that has some unique properties. In our case, for example, instead of relying on the chemistry of the material itself, we rely on the geometrical arrangement, on the material architecture and functionality. We combine this metamaterial with some special actuation techniques so that we could have properties that are intrinsic of materials, for example, materials that have deformations, or properties that we see, for example, in robots that have mechanisms that move as a rigid body mold and things like that. So we could have a material that behaves like a robot, or a robot that behaves like a material, or a combination.
Somewhere in between.
Yes.
Why is origami an interesting engineering approach?
Because origami is a fascinating technique to transform just a single piece of paper, for example, with a single operation only, just folding, this is a fold, into amazing three-dimensional configurations. Or we can also use a combination of folding and cutting, for example. In general, in the literature, whenever you cut, then you say kirigami, but in general, overall, origami and kirigami, they are basically the same family of origami type systems.
What are some of the benefits of using that approach with a robot?
In the Nature paper, we indicate that before, for example, there was a paper in Science in 2017 where they created a chiral system that had some very interesting properties, coupling the uniaxial deformation and the twist. But that could only work with small deformations. Then what we did was to use what is called the Kreslin origami, that is a unit like this. And then from here, we created a rod-based system, because this one is made of paper and those are all shells. Then we created an equivalent rod-based system, and then we assembled them properly into columns, and with a very precise control of the chirality. For example, this unit has the same chiral orientation. It's always here. The inclined valley is oriented this way, and then we can also do the opposite. And then we combine it with some rotating square mechanism that works like this, so that we could have a metamaterial that would allow us to have multimodal deformations and control this axial deformation and the twist in very unique ways.
With your modular chiral origami metamaterials and the meta robot, how might you control it? Do you have to do it with your hands, or are there other techniques?
The most natural way to actuate is with the hands, right? That's what I am illustrating here. But for the system to go to actual applications, then we need to have different means of actuation. In this paper, we used two different ways. One was a mechanical system. That's what we have, for example, in an Instron machine. We have developed special fixtures that allow us to explore this uniaxial end twist coupling and the chirality. The chirality is essential in this system. So that besides the hand, then we use a mechanical system. And the final one, that's the one that we are very excited about, is the magnetic one. Because the hand involves contact. You can see here, my hand is touching the endpoints of the crescent tower. The mechanical actuation also involves contact. It's like you put the system in a strong machine, there will be contact. However, with the magnetic actuation is a non-contact system, and then makes the metamaterial or the robot extremely elegant, very light, with unique properties that if you would actuate in different ways would become more difficult to achieve those properties.
Now that we've set up kind of how it works, how you might control it, what are some of the potential real-world applications?
There are many applications. Maybe one that relates, for example, to civil engineering, thermal regulation of buildings. Now it's very hot. What do we do here in the office or where you are? You turn on the air conditioning, right? And then in the winter, what do? We turn on the heater. But the cooling and the heating systems, in most houses I know, including mine, they are two completely different things. Now, suppose that, again, this is a prototype. This would be a panel of a building. Now, if you just take a look here, you can see that the dominant color that you see is black, right? And then because this is an absorbing panel, then this can be used to heat the environment. Now, the same configuration, for example, if I go and I actuate, now you can see that in this region, the dominant color is white, right? There is very little black. And then if I keep, for example, if I really want to cool the entire thing, I keep actuating them, right? And keep going. And this is, again, I am using my hands, but we develop a system that we can actuate all of them with a single degree of freedom, okay? And not my hand. But this is a prototype. Now, you can see that this now could be used to cool the environment. And what we have shown in the paper, this is figure 6 of the paper, is that this is exactly this system that I just demonstrated to you. You can see in the paper that it can vary from 27 degrees centigrade to 70 degrees centigrade. When black dominates the solar absorbing panel, then the temperature is higher. When the white dominates, then we have a passive radiative cooling effect, and then the temperature reduces. This is one application, and there are many others that we indicate in the paper. Robotics, right? Metamaterials. Also information encryption. And we have one example, because each unit is like, has a folded state that we can call here 0, or a deployed state 1, and then they can combine. And then we can have, we can control the bits of the Kreslin units in many different configurations that could lead to a mechanism for programmable information encryption. And something that we are very excited about is the non-commutative states of matter. If we pick up a piece of rubber and we fix it, let's say, on the left, and on the right-hand side, we twist in one way, let's say, counterclockwise and then clockwise, then it will come back to the original configuration. But because the sequence of actuation will matter if we invert that sequence. Instead of doing, let's say, clockwise first and then counterclockwise, then we do clockwise and then counterclockwise. Then the configuration of the system might be different.
So I want to refer back to your heating panel example that you showed, because I think that really connected the dots, at least in my thinking, for how you could potentially have a magnet system where you could flip a switch, and if these were all on the side of a building or something, it could dramatically change the experience inside the building.
What you said is a very good idea, but in a building, if you create a magnetic system, it can interfere with cell phones, with other things, and waves and so on. And then what we did was to create a mechanical system with 1 degree of freedom that could actuate all these units at the same time.
What scale would they need to be for a building? Would you want them much larger?
We only have a prototype, as you can see here, the scale of my hand. But then for a building, then this would be on the scale of the wall, right? Several meters. That's what technology transfer would be, to transfer things that we develop in a laboratory to a commercial scale application. Then we would have to design the units to be as minimally invasive as possible, and so that you don't use too much space in the panel. And then one way that would make it easy to use, for example, is to have it always on its maximum capabilities. Like what I showed you, all the units are folded or all the units deployed. Although you can have intermediate states, but then the actuation, for example, if I just want to actuate this one, would be more complicated. But if we want to actuate all of them at once, and this makes sense because, for example, right now it's really hot. Then you would if
you would want the maximum amount of effectiveness.
You want the maximum cooling that you can get. That would be the white surface, right? And in the winter that would be the opposite. And but then it would be in the meter scale, depending on the size of the wall that you want to cool down or to warm up. Would be a few meters on each dimension.
I would like to segue into some of your other work from here. And I know you're working with the concept of Tensgrity with Metamaterials now. Can you explain a little bit of what that might be?
We have been working for a long time in trying to create a duality theory where when we have an origami like this one that is based on shells, then we could have an interpretation of this origami in terms of a Tensgrity. What is a Tensgrity? We like what is called a class 1 Tensgrity. That is essentially, the best example would be a soccer ball, because we are having now the soccer championships, right? And there will be the World Cup in the future. Then the analogy between a Tensgrity and a soccer ball is the following. Is that, for example, if we have a spherical Tensgrity, then we would have cables that would be in tension, that this represents the membrane of the soccer ball. And then inside, we would have columns that would be in compression, and this would be an analog to the air that keeps the soccer ball inflated, okay? And then we are presently working on a theory that we call invariant dual mechanics of Tensgrity and origami. And this is a work in progress that allow us, for example, if our theory is right and if it works, by understanding, for example, origami, we could create some new Tensgrities, and vice versa. By understanding the Tensgrity, we could create a new origami systems, and this could allow us, although we started this research thinking only about regular structures that are very regular, as you can see here, that have like polygonal formations and so on. Also, this offers us a mechanism to create irregular structures, okay? Like structures that you see, for example, like the ones that ants do, for example, extremely irregular.
I want to ask you about your experience with NSF. What difference has NSF support made to your career?
NSF is tremendous. NSF, they are very open and they fund fundamental ideas, fundamental research, and a lot of the original developments in my own research program, they were supported by NSF, like this paper in Nature. And I hope that the support for NSF continues. Is a tremendous important agency in the United States. It works extremely well. I also worked at NSF some time ago as a program director between 2009 and 11. NSF is more than the sum of the parts at NSF is bigger than the whole, because NSF is structured in many different divisions, directorates, and related to different areas, but it also connects very well with the other agencies like the NIH for health-related research, with the Air Force, the Navy, the DOE, DOD, and all these agencies. And at the end, the way I see is that the sum of the parts is much bigger than the whole, and the NSF provides this unique vision where the fundamental research in any area is appreciated and welcome, and also leads to applications that they allow you to connect with other agencies, for example, translating some of the fundamental research toward application. NSF is amazing. It had a tremendous impact in my career. Without NSF, a lot of some of my best work, including this one I just talked to you, probably we will never know, but probably would not be done, or would have been very difficult to be done. NSF is amazing.
The last question I want to ask you today is, you mentioned that you're working on some Tensgrity materials for your next project, but I want to ask you kind of broadly, where do you see your work going in the next few years?
Yes, the duality between origami and Tensgrity, I think this opens a tremendous. If this works, and this is a work in progress, but if the ideas that we have work, this will offer a new paradigm in structural and material design for ordered and disordered materials. Another area that we are very excited about is that we started to work in this Nature paper is the non-commutative states of matter, okay? And then exploring these concepts of chirality and non-commutativity to create, for example, unique robotic arms, for example, or a robotic leg that could become lighter, more efficient, and more controllable by exploring the intrinsic architecture of the material or the structural system. And another idea that we are also very excited, but is a work in progress, is the idea to create origami state machines for programmable logic and memory that extends the preliminary ideas in this paper for programmable information encryption. So these are some of the ideas that we are working on right now.
This is an interesting area. The idea that you could use that for encryption and codes, like as a physical thing, is interesting.
Yes, and we are, and one of the key ideas to make this origami state machine work is to be able to actuate it in a very sophisticated way and in a non-invasive way by means of the magnetic fields, because you need no contact. If this is successful, Nathan, this is, for example, a system that cannot be hacked. If it is electronic, then this depends on the smarter hacker, right? Because it's electronic. But this one has a mechanical component, and then in theory could not be hacked. But this is a work in progress.
Right. Maybe like a combination lock. If you did it the right ways, you could figure it out.
Exactly.
But really, you'd need to know what it is.
Exactly. Yeah, but for example, we are doing some preliminary work in the lab. For example, we can do this state machine with thousands of combinations or millions of combinations, and then how are you going to find the right one? It's very unlikely. If a hacker tries to hack it, it's very unlikely.
Special thanks to Glaucio Paulino. For the Discovery Files, I'm Nate Podker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.